Now let me show you how it works in reality using an example. I took this example from NIST book on statistics. You can also find a similar example from the Montgomery book, and of course you are going to use your mini project to do the same, so you will have your own example. But let me show you the first of all this example from the NIST book. So how to implement the method of steepest ascent, all particular steps. Okay. Then these are all the steps. You can see that actually we have 7 steps. The last one, step number 8, it's a responsive phase design. It's something we are going to talk about the next time in the next learning sequence, in the last learning sequence. And you can see that I made it in 2 blocks. So we have some preliminary step here, and then we have 2 blocks. This is block number 1. Block number 1 aims at find actually if you can do the method, if you can actually run the method of steepest ascent. Then block number 2, it's actual run of the method of steepest ascent. Okay, so you have some preliminary preparation, and then you have the method of steepest ascent. Okay, so let me show you everything just step by step. Okay, well, first of all, you remember you always start with you use full or fractional factorial design, and you find these 2-3 most important factors. And in this case, I'll just show you the same example I showed you before. It's an example optimization of the yield using 3 different factors: temperature, concentration of catalyst, and the catalyst type. We used this example in a lecture on full factorial design. Then you remember we found out that actually only 2 main effects are important. It's temperature and the concentration of catalyst, plus you remember we have also the interaction between the temperature and catalyst type, right? So this is the ANOVA result. So we can see, X1 is important, X2 is important, and then what about the interaction? Interaction just tell us which catalyst type to use, right? So if you look at the plots, you remember that actually if you use catalyst 2, this is the interaction plot, this is the interaction plot. And then you can see if you use catalyst 2 is here, right? It's right line. So you can reach the higher yield than if you use catalyst 1. And then now we need to keep only the selected factors. So now we should get rid of all factors that are not important. And how to do that? Well, that's simple. You either, like in our case, you know which levels you need to use for this non-important factor. So in our case, you remember it should be level B, right? Catalyst of type 2. And then look, you simply take all values for the level B and get rid of the other values. So that will be your matrix for the method of steepest ascent. Okay, so we just took only temperature and concentration of catalyst, and we took average values for all these combinations. And then in this case, we simply selected all experiments with catalyst B. We know that catalyst B gives us higher yield than catalyst A. Okay, but sometimes, of course, you don't have this clear effect, clear interactions. In this case, you simply take an average. So for example, you take the same levels for important factors. In our case, we start with 160 and 20. So we have 2 sets of experiments, 4 runs for 160 and 120. And we simply make an average for Y value for this combination 160 and 120. And then we do the same for the next level, 180 and 20. We do the same for the next, then we do the same for the next. So in this case, we also will end up with this small table that includes only results for full factorial experiment from the most important factors. Okay, so what to do next? The next, you need to do the following. You need to take these values. So these are the values, and I will use these 2 representations. One is the real values, and one is coded values. So we use -1 and +1 to code the values, right? And then now you need to test the following. Are you indeed on the side of the hill, right? So if we make a hill like this, are you indeed here? Maybe you're already here. How to test it? Well, the point is, if you are here and if you make this, for example, the full factorial experiment, you will see a curvature, some curvature here. Right? But if you're here, you don't see any curvature. So the points line exactly on the plane. So that's the idea. You need to test if you have any curvature effect in your data. How to test it? Well, first of all, think if you have only full factorial design like this one. Of course, you cannot see any curvature in this case. So what you need to do, you need to add a central point. And if central point is significantly higher or lower than for example, the corner points, the factorial points, then you have a curvature. Then you can make a statistical test how significant this curvature effect is. Adding central point gives you another advantage. actually you can make like 5 or 4 experiments with central points, and then you will see some variation of your y values, right? And then you can use this variation to estimate the standard error of your effects, right? So you can estimate this how big the variation, the noisy variation is. Because you don't have variation on the corner, you can use the central point to find this variation. So you will have a good estimate for standard error, even though you have only like a small amount of experiments, okay? So we use central point, experiment with central point for 2 reasons. First of all, to test the curvature, for testing a curvature, and second, to give an idea how big actually the random variation of our response is. So we can use this estimated standard error to see if effects is significant. Okay. Now let me show you how to do that. We simply add the several experiments with central point. Usually we use 5 experiments to have enough degrees of freedom. So we need to run our experiment with this, for example, in this case is 200 Celsius degrees and 200 minutes, 5 times, and make sure that you run them. You try to randomize something at least. You don't use the same sample, so you prepare samples separately. Maybe you use different, for example, different devices to make measurements, different devices to mix your sample if you need to mix them, and so on. Okay, so make sure that you have a proper randomization. Okay, then I did it. So I ran of course, I used the results of experiment from this source I mentioned. So this is the yield we got for these 5 experiments with a central point. Okay. Now the point is we can use these 5 values to, first of all, to test for the curvature and also to estimate the standard error of the effect. Okay. So how to make a curvature test? The idea is similar to ANOVA. We need to look at the variance for the central point, and we need to look at the variance for the corner points, for the factorial points, and see if ratio of these variances is different or not. So it's very similar to ANOVA, where we also analyze the ratio between systematic variance and the random variance, right? So that's how it works. So we split our data into 2 parts. We have y values for factorial design, and we have y values for the central point. And first of all, we estimate noise. And this noise we estimate in a simple way. We calculate variance for all central experiments. Because we have 5 experiments, and we know that these experiments, we use the same conditions, the same values for x1 and x2 in these experiments. Therefore, we can use the variation of yc simply as an estimation of the standard. Okay. Then we can calculate the signal ratio. The signal ratio, it's a difference between average value for central point and average value for the factorial design. And then we also use degrees of freedom to make the correction for how many experiments we have. And then look, we simply take a ratio between this signal variance for the signal and then variance for the errors. And this ratio between these 2 variances will be our signal to noise ratio, or F value. Then you remember F value follows F distribution. We can calculate a P value, and then if P value is quite large, our null hypothesis in this case is no effect, which means that there is no curvature effect. We don't have any curvature. We are on the side of the hill. And then if P value is small, of course, we reject null hypothesis. So it means that we are on the top probably, or close to top, so we have a curvature. But if we don't have any curvature, we simply can continue our steepest ascent. Okay. Let me do the calculations. So first of all, I estimate the number of values. For factorial design, we have 4 values, 4 corners. For central point, we got 5 values because we repeated this experiment 5 times. And then I calculate the average y for factorial experiment and average y for central point. And you can see we have a small difference, but if we make a plot, so you can see the blue here, these points are for central points, these points are for factorial points. So you can see that also this is the average. So lines show you the average. So you can see even though we have a small difference of the average, it doesn't seem to be significant because the variation of central point is quite large. Okay, so I'm pretty sure that if you run this test, we will not see any curvature here. And indeed, this is the variance for curvature effect. This is variance, the total variance, the random effect. And then this is the F value. So you can see the F value is pretty small. Okay, so the ideal F value for no effect is 0. Then you may have 1 or 2, but in this case it's very close to 0. So if you, for example, this is F distribution for our degrees of freedom 1 and 4, then if you calculate the P value, you will get 0.72. So in this case, we stick with null hypothesis. There is no curvature effect. So it means that we can continue and use method of steepest ascent to climb the hill. If we have a curvature effect, we stop here and jump to the next part, which is a response surface design, which I'm going to talk about in the next learning sequence. Luckily, we simply continue. In this case, so we are on the side of the hill. Now we can just run the method of steepest ascent. Okay.